Alright students, we're going to make a quick video on logistic functions. So here it goes. There's going to be a lot of background noise, I apologize, because there's students in the classroom. Anyway, what are logistic functions actually started because of a lot of concepts that we learned from Charles Darwin and things that happen in nature. So let's take a look at an example. So a species of fish has a population in year 0 of 500 and 600 in year 1. Let's determine the growth rate and population using both linear and exponential functions. So here are our linear functions and our exponential functions, and these are the recursive functions here, and these are the general explicit functions here. And this is how we find, say, the rate of change in a linear function or the growth factor in an exponential function. So first off, the linear function, if p sub n is 600 and p sub n minus 1 is 500, then that rate of change, that d, is 600 minus 500, so it's just changing 100 per period. So the linear function would just look like that. It would be 500, then 600, then 700, then 800, then 900. Now, if we wanted to look at an exponential function, the recursive function, this 1 plus r, or even in the general form, the explicit form, 1 plus r is simply p sub n divided by p sub n minus 1. And so this is showing us that it's growing by 20% from year 0 to year 1. So if this exponential growth rate continues, we would just multiply it by 1.2 every time. So 500 times 1.2 is 600, times 1.2 is 720, times 1.2 is 864, times 1.2 is 1037. So what happens if there's like some sort of shock in, year 1? After year 1, and then all of a sudden there's only a capacity of 900 fish after year 1. Say, there's an oil spill in their pond or something like that, and then all of a sudden you can only fit like 900 fish in that pond. Then we would actually need to use a logistic function to calculate that. And how logistic functions work right here. And this is the recursive version of a logistic function. And so p sub n equals p sub n minus 1 plus r times this 1 minus the p sub n minus 1 over k. And k is our capacity constraint. So in this case, it would be 900. So let's take a look at an example how we would calculate this. And r is just our growth rate of 20%. So if we're starting in year 1 at 600, and we know this is a 20% growth rate, and then what's going to happen is I'm going to multiply this 20%. So we have the 600, that's our 100%, plus 20%, but that's going to get reduced by this factor here. And so 1 minus this fraction of 600 divided by 900 times the 600. So we can plug that into our calculators, and what you're going to see is this. So year 2 is going to be 640. So let's go ahead and write that in there. So as you can see, it's actually growing at a much smaller rate than what we had here with this exponential growth. So what's going to happen is it's going to actually approach that 900, that capacity constraint. And so what's that going to look like graphically? Oh, and one thing I wanted to point out is here, this function. If you notice this function here, this whole thing, just imagine, right, as this number gets bigger and bigger and bigger, this 600 in the numerator, this p n minus 1, so as this number gets bigger and bigger and bigger, this fraction is going to approach 1. What's 1 minus 1? Well, that's 0. And so anything times 0, so I'm multiplying this whole expression here by 0, it's just going to stop changing, right? So this Pn minus 1 is going to just get, this change that you're going to add to it is just going to get smaller and smaller and smaller. It's going to approach 0 over time. So that's why it just approaches, it has a limit of that. So yeah, it just has a limit of whatever that capacity constraint is. So in this case, the limit is 900. And so we'll see what that looks like graphically. So let's take a look again. Here are the solutions. So we have those. So you can make sure you note those down on your notes. And so this is what a logistic function looks like graphically. So here's the exponential function. So a linear function would just, look something like that. And then this logistic function basically has a capacity constraint of, in this case, this is a different graph, but this is the capacity constraint in this example would be 10,000. So if you think about like a fish population, it's going to approach that, and that's what's known as a limit. It's going to approach that limit but never really reach it. But we do see examples of these logistic functions actually breaking through the capacity constraint. And so I'm going to show you a couple of other examples graphically. So for example, like if the growth rate were really, really high and you were already near the capacity constraint, so say like for some reason you were like right here, and then all of a sudden there was another shock to the ecology system, like say, I don't know, some species like just died off because the water got too warm from global warming or something like that, and these other fish that fed on that like are starting to die off, so their capacity constraint is actually restricted because they'd have a smaller food supply. So what's going to happen is it's going to break through that barrier and then come back down and then break through it again. And so mathematically you would see that in that formula. It would actually kind of give you this sort of diagram. And then it could even have a bigger shock, which would like cause a more dramatic decline, and then it would approach it again, and it would continue to approach that K, but it would actually alternate sides. So it's really an interesting example of this, and we see this in science and nature all the time. Like anytime there's some sort of shock to an ecology system, then it'll overshoot and then massively degrade. And so like that's really how like these endangered species, like what happens to their environment, it can dramatically drop off, because what happens is it overshoots because their capacity is like dramatically diminished, and then the species will drop off very quickly. So anyway, I hope this helps. Please let me know if you have any questions. This is an application that you'll see in a lot of areas of science and economics and other sorts of things, and actually in apparently in technology and like capacitors and things like that. Anything that has any sort of constraint, you'll see kind of functions kind of like this. So have a nice day. Look for my next video. My video's done. Yay! Thank you guys.